Good morning, dear students. I am Dr. Akhil Gupta. I am faculty member at Department of Electrical Engineering, Punjab Technical University. And today, being the first day, I welcome you all on behalf of Punjab Technical University. I know you are belonging to the different streams: computer science, mechanical engineering, and civil engineering students. So, dear students, for your information, I will teach you the basic electrical engineering course in this semester. So basically this basic electrical engineering course we normally teach to the first and second semester students. So dear students, it is my foremost duty to let you know why you should study this subject. Being the civil engineer, it becomes very important in the designing, installation and maintaining the various electrical systems and all the electronic equipments in building projects. Being the mechanical engineer, uh, some products and industries are very heavy. So, especially in the electromechanical energy systems, so education of the basic electrical engineering is very, very useful for the mechanical engineer. Similarly, for the computer science and engineering students, the understanding of the electrical engineering basically provides a strong foundation in underlying various hardware systems that powers the computing systems. So you can see the syllabus. You can see the whole syllabus has been divided into the four modules: DC circuits, AC circuits, electrical machines, and the electrical installations as the module number 4. So this complete basic electrical engineering course has been divided into the four course outcomes. The first course outcome that we will be having the knowledge of the DC circuits and the various types of the AC circuits. We will be also learning the basic magnetic circuits, which will be very useful in understanding the basic principle of the AC and DC machines. And we will be also learning the various components of the low voltage and high voltage electrical installations. Course outcome number 2, that we will be able to analyze the dynamics of AC and DC circuits. Course outcome number 3, that we will be understanding the basic magnetic circuits and their applications in various electrical machines. In the module number 3, you will see that the electrical machines has been divided into the two categories, AC and DC machines. So this magnetic circuits is very much common to both AC and DC type of electrical machines. Course outcome number 4, that is your final outcome, we will be learning in module number 4 the various types of wiring systems, earthing systems. We will be learning the classification of batteries and their characteristics. And finally, we will be completing the study of the module number 4 with the discussion and analysis of the low tension switchgear systems and associated protective devices. So, students, uh, uh, I will be suggesting the books also. The basic electrical engineering, you can study the basic electrical engineering by D.P. Kothari and I.J. Nagrath. Then I will be recommending Edward Hughes, Electrical and Electronics Technology. The publisher is Pearson. And third one, I will be recommending Electrical Technology by B.L. and A.K. Tareja. For this, the publisher is, you can see, S. Chand Publishing. Also, you can refer Basic Electrical Engineering by J.B. Gupta, S.K. Kataria and Sons. So here students, first of all uh, I will be starting with the discussion of the uh, resistors. So in electrical systems, we will be finding there are two types of components, active and passive components. In active components, you will be finding the uh, examples of diodes, transistors, various types of FETs, whereas in the passive components, there are the three categories. First one is the resistor, second one is the inductor, and third one is the resistor. So students, being the first day, let us study the basic discussion of the resistor. What is a resistor? A resistor is an electrical component designed explicitly to have a certain magnitude of resistance. Its unit is ohms. So you can see it is a two-terminal passive electrical component that represent the resistance of the electrical circuit. Its function is to provide the opposing force to the flow of electric current. So it must operate reliably in the environment, including the electric field intensity, varying temperature conditions of humidity, radiation, and other effects. The examples of resistors you will be finding in the motor starting resistors and the resistors used in electronic amplifiers, which helps in controlling the overall gain and other characteristics of the amplifier. Second topic of the today's lecture is the Ohm's law. Ohm's law, dear students, I think you might have taken this discussion of Ohm's law in your junior classes. This Ohm's law definition is not new. The definition will be same. Rather, we will be learning the application of the Ohm's law in this semester. We will be able to analyze the various kinds of AC and DC circuits and study how the outcome of the Ohm's law is changed when we study the any kind of electrical circuit under the different loading patterns. Okay. Uh, Loading patterns, I mean to say, for example, in our home also, we have the different types of electrical loads in terms of electric fan, refrigerator, air conditioner. Okay, so these all energy consuming devices comes under the different types of load. On the commercial side, you will find the electrical motors, you will find the electrical motors, generators, geysers in the heavy industries. Okay. Similarly, on the agriculture side, you will find the applications of the AC and DC motors. Oh, okay. In the electric traction systems, you will find majority of the cases the application of DC motors. Okay. So, dear students, let's come back. What is Ohm's law? So, if we take a simple circuit, okay, so dear students, you can see at the right hand side of a we have taken a simple circuit consisting of a 10 ohm resistor. Okay, to a 10 ohm resistor, we are applying the input voltage of 10 volt DC. Okay, so this 10 volt DC is basically the input supply to the 10 ohm resistor. So 10 ohm resistor is basically acting as a load. Okay, so in between the 10 ohm and the 10 volt DC, you can see the wiring system. This wire has some resistance. Okay, so ideally we ignore this. Ideally we ignore the resistance of this electric wire connecting the 10 volt DC to the 10 ohm resistor. But in the ideal conditions, but in practical conditions, we must not neglect the resistance of the wire because every wire has some non-zero resistance value. Okay, so what is Ohm's law? So when the current I in a conductor is steady, the meaning of steady is constant. Okay, and there are no voltages within the conductor. The value of the voltage V between the terminals of the conductor is proportional to the current I. You can see when you open the proportionality constant, we are getting the another constant, that is R. This constant R is known as the resistance of the conductor. Okay, you can see also the one type of resistor with for the value of which we can calculate with the help of the color coding. Okay, so you can see the schematic of the small resistor where we are having the different types of colors. Although it is not visible here, you can see that you the left hand side, if we are finding black, brown, we will be able to calculate the value of the resistor with the help of the color coding of the resistor. Okay. Then in the category of the Ohm's law, we are having the another subtopic cylindrical conductors, for which we are able to calculate the resistance using the formula L upon A. That is, the resistance is directly proportional to the length of the conductor and inversely proportional to the area of cross section. Area of cross section, we know the common formula, that is pi r square or pi d square by 4, where r is the radius of the conductor and d is the diameter of the conductor. Okay, so in this formula to calculate the resistance of the conductor, the constant rho is known as the specific resistance of the material. It is also known as the resistivity of the material. You can calculate the unit of the resistivity also. You can cross multiply R with A, that is, you get ohm into meter square divided by length, that is meter. So eventually we get the unit of the specific resistance, that is ohm into meter. So this you should remember. This is a very important parameter in the electrical engineering. Rather, it is very helpful in finding the resistivity, how much specific resistance of the wire connecting the load with the input source. Next, it becomes important for us that how the temperature varies with resistance. The formula is given by RT2 is equal to RT1, ब्रैकेट में आएगा आपका 1 plus alpha T2 minus T1, where we are able to calculate the varying resistance under the ambient temperature conditions. Okay, so the resistance of the conductor always vary with the temperature. For a good conductor, it is directly, the resistance of the conductor varies in direct proportion with the temperature. Whereas in case of the semiconductor and the insulator, the resistance of the conductor is inversely proportional to the temperature. Inversely proportional means whenever the temperature increases, the resistance of the conductor decreases. So the resistance of the metals and the most of the alloys increases with temperature, whereas the resistance of the carbon and the electrolytes decreases with temperature. Okay, for usual conditions, as for about 100 degrees Celsius change in temperature, the resistance at a temperature T2 is given by this formula. This formula, students, you should remember when we will be attempting various numerical problems in the tutorial. Okay. So, see students, the Ohm's law is not applicable to nonlinear circuits. It is applicable only to linear circuits. Okay. So, dear students, you must remember all semiconductor devices are the nonlinear devices. For example, diodes, transistors, field effect transistors, MOSFETs, IGBTs, all are the semiconductor devices. For these semiconductor devices, the Ohm's law is not applicable. That is, Ohm's law is applicable only to the linear circuits. It is not applicable to the nonlinear circuits. The second limitation of the Ohm's law is that the temperature of the system must remain constant. Okay, the temperature should not vary. We should not analyze the outcome of the Ohm's law under the ambient temperature conditions. The second component of the passive devices is the inductor. Inductor is a circuit element whose behavior is described by the fact that it stores electromagnetic energy in its magnetic field. Now, electromagnetic energy, the concept of electromagnetic energy you might have taken in your 11th standard. The electromagnetic energy you had estimated numerically also. It was half Li square, where L is the self-inductor and I is the current flowing through the electric circuit. In its common elementary form, inductor is formed by winding a coil of wire, often copper, around a form that may or may not contain the ferromagnetic material. At the bottom side of this slide, you can see a small inductor across which we are applying the voltage VE. You can see the polarity, that is plus and minus sign. And you can see, note down the direction of the electric current. You remember always, students, the electric current always flows from higher potential to low potential. In this case, the higher potential is indicated by the plus sign, whereas the lower potential is indicated by the minus sign. So this behavior is mostly analogous to the flow of water. You can see you always see in the real life that water always flows from higher height to the lower height. Similarly, the electric current always flows from higher potential to the lower potential. Okay. Then second most important thing is that the voltage drop across the inductor is estimated by the formula L di by dt. L is the constant which is known as the coefficient of self-induction, that is self-inductance, and di by dt is the rate of change of current. Always remember, dear students, that the unit of self-inductance is Henry. So, what is inductance? It is the property of the conductor that is useful in circuit analysis. So, the voltage across the inductor is estimated by the formula L into di by dt, and if you cross multiply it, that is V into dt is equal to L into di, and di is coming out to be 1 upon L into V dt. So if you integrate both sides, the eventually we will be getting the electric current flowing through the inductance. That is, I is coming out to be 1 upon L integral of Vt into dt. At the right hand side, you can see another constant term, that is I0. I0 is a constant term. So, whereas 0 indicates that this is the initial current, okay, T is equal to 0, which is always a constant. In most of the numerical conditions, they either it will be assumed to be 0, or the examiner will be giving you its numerical value. Then another formula to estimate the energy stored in the inductor is half Li square joules, where L is known as the coefficient of self-inductance, I is the current flowing through the coil of wire, and V is the voltage across the inductor. Then the part of the inductor is the mutual inductance. This is the second type of inductance between the two magnetically linked coils. Okay. So if the two coils are wound on the same coil form, or if they exist in close proximity, the meaning of proximity is that the two coils must be placed very near to each other. Okay, so that the mutual flux links with the both of the coils. Then the changing current in one coil will induce the voltage in the second coil. So this sentence is applicable in vice versa conditions also. The changing coil in the second coil will induce the voltage in the first coil also. Okay, so this is applicable as vice versa condition. So this concept of the mutual inductance is applicable to the case of the single phase and three phase transformers. Okay. Uh, the unit of mutual inductance is same as that of the self inductance, that is Henry. Then third type of passive component is capacitor. You know that capacitor is an electrical component which helps to store the electric charge. Okay. So in its simplest form, the capacitor is composed of two conducting plates which are separated from each other by a medium. That medium is known as dielectric medium. Numerically, the charge is estimated by the formula C into V, where C is the capacitance. It is always given to us, and rather it is always mentioned at the surface at the top side of the given capacitor in the labs. And V is the voltage between the two conducting plates. The unit of capacitor is farads, microfarad, nanofarads, or picofarads. On the similar patterns, you can estimate the energy stored in the capacitor also, half CV square. Okay, and the current flowing, that is I is equal to C dV by dt, and the voltage across the capacitor is 1 upon C integral of IT dt plus V0, where V is 0 is the initial condition voltage at time t is equal to 0. Okay, so it is always given to us, or in the numerical problems it is assumed to be 0. Then over to the second next one, that is what is power. Okay, in electrical engineering students, I will be discussing with you there are three types of power. Okay, the unit of power is watts. We always know that. That is joules per second. The power delivered by an electrical source to an electrical device is estimated by the formula V into I, where V is the voltage developed between the two terminals and I is the current flowing through the electric wire. So if the device is a resistor, then the power delivered to the device is given by the various equations applicable for DC and AC circuits. For DC circuits, the power is estimated simply by the product voltage into current, whereas for AC circuits, we have the two different formulas VI into cos theta for single phase circuits, and for the three phase circuits, we have the formula root 3 VL cos theta, where cos theta is a very important parameter in electrical engineering. That is known as, this is known as the power factor of the AC circuits. The normally maximum value of the power factor is considered to be 1. For a good electrical power circuit, normal value of the power factor is chosen as between 0.88 to 0.92. Okay, that is, the value of the power factor is always less than 1. Okay, it can't be more than 1. Okay, it can't be more than 1. Why? Because it is a ratio of the two similar parameters. Okay, so since it is a ratio of the two similar parameters, cos theta is dimensionless, it has no units. Then the next one is, dear students, it is energy. Okay, so energy, it is very much related to power. So as I mentioned earlier, that power is basically defined by energy per unit time. If you cross multiply it, you will calculate the energy by the product of watt power into time. Okay, you can see here the energy is estimated by the product of power into time, where power is calculated by the product of voltage and current, and time is indicated by dt. Okay, so the SI unit of the energy is joules. Okay, but in commercial side, we have the different unit of energy. If we see our electricity bill, you will be finding uh, the unit of the energy as 1 kilowatt hour. So 1 kilowatt hour is basically one energy unit. Okay, so if you convert 1 kilowatt hour in joules, it is coming out to be 3.6 into 10 raised to the power 6 joules. Okay, the formula is very simple. Kilo means 1000. Kilo means 1000. What is the definition of watt? Joules per second. Okay, so 1 kilowatt is 1000 joules per second. And how many seconds are there in 1 hour? That is 3600. So if you multiply 1000 into joules per second into 3600 seconds, you will be getting 1 kilowatt hour is equal to 3.6 into 10 raised to the power 6 joules. The next topic of today's presentation is Kirchoff's law. Kirchoff's law, there are two types of Kirchoff's laws. One is Kirchoff's current law and second is Kirchhoff's voltage law. We will be taking the explanation of the Kirchhoff's current law with the help of a simple electrical circuit that is indicated by uh, in this figure. Kirchhoff's current law says that the sum of currents approaching at any node is equal to the sum of all currents leaving that node. For example, in this electrical circuit diagram, if we are considering the node number 1, for this node number 1, the sum of incoming currents is equal to the sum of outgoing currents. Sum of incoming current means the current which is generated by 30 volts DC source and the current, and this current is approaching the node number 1. Outgoing current means the current which is leaving the node number 1 and flowing towards node number 2. Similarly, another outgoing current is leaving the node number 1 and approaching the node number 3 through the 1.5 ohm resistor. So Kirchhoff's current law says that incoming current, that is input current, is equal to the current flowing from node number 1 to 2 and the current plus the node current flowing from node number 1 to node number 3. So this is the Kirchhoff's current law basic principle. So in this schematic, 30 volts DC source is basically acting as an energy source, and 1 ohm resistor which is connected at the extreme right hand side of this electrical circuit diagram is constituting the load. Okay, if you add the 1 ohm resistor, 1 ohm resistor and 1 ohm resistor, because all these three resistors are connected in series, this constitutes the electrical load for the electric circuit diagram. And in between the 30 volts DC source and the 3 ohm load resistor, you will find this the system. So the system is represented by the different types of the resistance values: 3 ohm resistance, 3 ohm resistance, 1.5 ohm, 6 ohm, 3 ohm, 1.5 ohm. So in between the 30 volts DC source and the 3 ohm load resistor, the the electric circuit is represented by the system. Let us come to the Kirchhoff's voltage law. This is another fundamental principle which is commonly written as KVL. In the equation form, it is written as V1 plus V2 plus V3 plus Vn is equal to 0. So how the Kirchhoff's voltage law is applied? For example, in the in this electrical circuit, we have the three loops. Okay, the loop number one is in the loop number one we have the 30 volts DC source, which is the input voltage, and this input voltage is basically the energy source for the remaining three loops. Okay, so whatever the voltage drop in 3 ohm resistor, 6 ohm resistor, and you see the at the lower side we have a 3 ohm resistor. Whatever the voltage drops occur in these three resistor values, it will be subtracted from the 30 volts DC source input. Okay, so in that case we will be saying that our Kirchhoff's voltage law is applicable. Okay, so I mean to say that Kirchhoff's voltage law, when you will be applying to loop number 1, will be will be calculated by 30 volt minus the voltage drop across 3 ohm resistor minus the voltage drop across 6 ohm resistor minus the voltage drop across 3 ohm resistor is equal to 0. Okay, so you can see this behavior. You can see the behavior of electric current when flowing from 30 volts to node number 1. Okay, you can see the 30 volts is the input, and at node number 1 we have the terminal voltage as 19.5. So when the electric current is flowing from input towards the load, there is a drop in potential which is calculated by subtracting 19.5 from 30 volt, that is 10.5 volt. So we can conclude that 10.5 volt is the voltage drop across the 3 ohm resistor. Okay. Similarly, you can see that between V2 and V7, at V2 and the voltage is the potential is indicated by 19.5, whereas V7 at V7 we have the potential is 10.5. So if you subtract 10.5 from 19.5, you can calculate the drop in potential across 6 ohm resistor. So it is approximately 9 volt. So you can see that the 9 volt is the voltage drop across the 6 ohm resistor. Okay. Now, the next topic of today's presentation is DC source. DC source and the AC source. Let us take first of all the DC sources. In the DC sources, you will find the batteries, they always deliver the constant current. Okay, they always taken as the constant voltage sources and constant current sources. So basically the DC sources means direct current sources, but it has come to stand for constant sources as well. So the figure shows the standard symbol and the electrical symbol for a DC source. In the electrical symbol, you can see that the plus polarity is indicated by the length of more length, bar of more length, whereas negative polarity is marked a bar of smaller length. Okay, you can see at the third electrical symbol where you can see a small arrow in a small circle. Whenever you find the small arrow, it always indicates that it is a current source. Voltage source is always represented by the two the two different vertical bars. Okay, the current source is always indicated by a small arrow in a small circle. Okay, so either there will be the voltage DC source or current DC source. Next, come to the AC source. AC means alternating current. Okay, in most of the electrical systems, likewise, we do have our domestic, commercial, residential, and agricultural systems. We always receive the AC electrical power. Okay, because AC electrical power is generated at the maybe at a distant thermal power stations. Thereafter it is transmitted, distributed, and finally we are receiving at our PTU campus and being utilized. Okay, so this AC source is always written in the form of a equation, where in this equation you can see small v, it is the instantaneous value of the voltage, small I, it is the instantaneous value of the current at a particular time. Instantaneous means at a particular time. So we do have the voltage and the current values at some different instants. Okay, and at the right hand side you can see the capital V. Capital V means maximum value, and this maximum value is indicated by putting the small m in the subscript. Cos omega t, where omega is basically 2 pi f. F is the supply frequency. In India, the supply frequency is always 50 hertz. Alpha is the phase displacement between the uh, voltage phasor and the current phasor. Then next definition is what is effective or root mean square value. And in the short form, we always say RMS value. The voltage we are receiving at our home, it is RMS voltage. Okay, it is not constant or DC voltage, dear students. It is the RMS voltage or it is the effective value. Okay, there is no difference between effective voltage, RMS voltage, or AC voltage. All these three terms have the same meaning. Okay, so in the RMS or AC systems, the average power is estimated to be I square into R, where I is the RMS value and IRMS is always calculated by the formula IM divided by root 2, where the value of root 2 is 1.414. So if you put this value of IRMS into the formula to calculate the power, we will be getting the value of the power as I square into R divided by 2. Okay, so this is the amount of the power which is identical to the power that is being delivered to the load by the constant DC current. So thus the effective value of AC current is equal to the maximum value, and it is divided by always root 2. The alternating formula to calculate the RMS value is indicated by under root of square root of integral of IT whole square into dt and divided by its time period. The time period you will be choosing whether you are taking 180-degree, one cycle, a half cycle, two cycle, three cycle, and so on. Next important term is the power factor. When the voltage across the device, when we apply the voltage across the device, the current is given by this equation Im cos omega t plus beta, whereas the voltage is calculated by the formula Vm cos omega t plus alpha. As I told you earlier also, where alpha and beta are the phase displacement angles, okay. So if you calculate the average power over the number of cycles, okay, by multiplying the small vt with it, you will eventually getting the final formula Vrms into Irms cos alpha minus beta. In this formula, the value alpha minus beta, it is known as the phase displacement between the voltage phasor and the current phasor. So when you take the cosine of this angle, it becomes a power factor. And this alpha minus beta is also known as the power factor angle. So this power factor is the measure of how effectively the incoming electrical power is being utilized in the electrical systems. So it is also estimated by the ratio of the real power or real power divided by the apparent power. So if the power factor is high, then we can conclude that the electrical power being generated is being used efficiently in the electrical systems. As I told you earlier also, the maximum value of the power factor is 1 because it is the ratio of the two similar parameters, and it is dimensionless also, that is it has no units. Okay. So the optimal value of the power factor is maintained between 0.88 to 0.92. Okay. So high power benefits both consumers and power company, whereas low power indicates the poor utilization of electrical power. In the electrical engineering, the concept of power factor is only discussed in AC circuits. The concept of power factor is not applicable to the DC circuits. Now we classify the different power factors according to the different types of loads. As I told you earlier also, there are three types of components: resistors, inductors and capacitors. Accordingly, there are three different types of loads: resistive load, inductive load and the capacitive load. The resistive load, for example, the light, electric heaters, they always operate at unity power factor. The inductive loads examples are induction motors at our homes, electric iron at our home, the electric fan at our homes. All these are the examples of the inductive loads. Here I will be adding the electrical motors which we are using at our homes, that is in our residences. All they are the single phase induction motors. That is why they comes under the category of inductive load. Thirdly, we have the capacitive loads where we have capacitor banks and the synchronous motors because they are used only for the improvement of power factor. Okay, that is why these capacitor banks and synchronous motors, they operate at leading power factor. Whereas induction motors, the application of induction motors, electric irons, they causes the low power factor, and that is why they are known as the lagging power factor loads. So in case of AC circuits, the value of power factor always lies between 0 to 1. Unity power factor means cos theta is 1. Cos theta is calculated by the formula R upon Z. You can see in a power triangle where we are indicating, where we are representing the real power by the horizontal line, and the reactive power is indicated by the vertical line, and the final power or apparent power is indicated by the hypotenuse in this right angle triangle. You can note down the angle theta which is marked between the real power and the apparent power. Okay, when you take the cosine of this angle, then it becomes a power factor, and this theta is known as the power factor angle, that is alpha minus beta in the previous slide. Real power is estimated by the formula Vi cos theta. Okay, and because in this power triangle, when you take the cosine, what is cos theta? Real power upon apparent power. So if you cross multiply, you will get real power as Vi into cos theta, because apparent power or total power is given by the formula Vi only. So similarly for the three-phase systems, the real power is estimated by root 3 into Vi cos theta. Similarly, if you take the sine of the sine of this power triangle, you will calculate by reactive power upon apparent power. So if you cross multiply, reactive power is equal to sine theta into apparent power, that is V into I. Similarly, for the three-phase system, the reactive power is estimated by root 3 Vi sine theta. Ideally, the coils don't consume any electrical energy, but it creates a significant electric current. So the real power, which is the power actually consumed in the resistive load, the apparent power is the power that the grid must able to withstand. The unit of real power is always watts, whereas the unit of apparent power is volt into ampere. The unit of the reactive power is volt ampere reactive. Similarly, we can draw the impedance triangle. This is the impedance triangle, which is clearly visible on your screen. In the impedance triangle, the horizontal part is indicated by the resistance, vertical part is indicated by the reactance, and the hypotenuse is known as impedance Z. So in the impedance Z, we always take the formula R plus jx, where R is the resistance and X is known as reactance. There are two types of reactance. One is known as the inductive reactance corresponding to self-inductance, and second is known as the capacitive reactance. You can observe the direction of the capacitive reactance, that is Xc. Its inclusion in the electrical power system is very much desirable because it helps in improving the power factor from lagging to leading one. Okay, so the application of the capacitors in the electrical systems improves the power factor from lagging to leading, and thereby it helps in consuming the electrical power effectively in the electrical systems. The formula for inductive reactance is omega L, where omega is 2 pi f. As I told you earlier also, in India the f is always 50 hertz. The capacitive reactance Xc is estimated by the formula 1 upon omega c, where omega is 2 pi into f. Few advantages of maintaining the high power factor. It helps in improving the voltage profile, and it helps in the reduction of variable losses into the electrical system. Thank you.